Good evening, everyone. This is part 2 of the Lab 8, Tuesday, October 14. And we're going to go over last part of the Lab 8. And the basis of that is calculating redshift and also Hubble law based on the simple calculation that is provided. Let me share with you the screen that we had for this lab. Just a second. Okay. It's the one that you see it here. Open up again. You see the screen?
No, black screen right now.
Okay, let me share it again. How about right now?
Not yet.
How about now?
Yep, there we go.
Okay, very good. Here on the Lab 8, the simple thing that we have, as mentioned, is last week we had the rubber band. We call it this one a rubber band one-dimensional universe. And we just give some indication briefly what the space expansion is, that and Big Bang is the explosion of the space, then the explosion in a space. That is concept that we had. The very simple example that we have it here is rubber band that we cut it around 18 centimeter, and we mark it 3, 6, 9, 12, and 15 on this rubber band. And we tie down the beginning and end, the first one and last one in the foam board, or a kind of card foam board that is very little bit thick to make sure that engage the uh, pins on the board. And then what those are representing is important here to notice. This is Galaxy 1, this is Galaxy 2, Galaxy 3, Galaxy 4, and Galaxy 5. Galaxy 1 is the location of we are assuming this one is location of the galaxy. And we're going to see how intuitively we just measure the distances based on the several model that we have for the universe to consider. But the only things that you're going to measure the number 2, 3, and 4 here, and also the 5 that at the end. This 0 or galaxy 1 is a kind of location of the origin that we're gonna consider. First, the idea is that when the distance between these two is about 15 centimeter, then we just take this one pin, last pin out, and stretch with the rubber band to reach to the 27. But we do it every minute 3 centimeter. It means that we take this one out and we stretch it 3 centimeter from here to here in about 1 minute. And then measure the distance, and we do the same thing on another minutes as well. Why we do that? And another important item, that make sure that you have safety glass, and also make sure that this entangled in angle pin to the foam board that doesn't disengage after the pushing the uh, operation when they expanding the universe. This is, we call it rubber band one-dimensional universe, or rubber band universe. And we see how we can easily, with this one-dimensional item, we can model and create a Hubble law into consideration. We have several data tables here on this lab 8. And the data number one is that universe expanding at constant rate. And what we're going to do here is the one that is here is a time from 0 to 9. And the reason that we're taking this one, for example, this is the distance between galaxy 1 and 5. Which one is the galaxy 1? This is galaxy 1 and this is galaxy 5. And then uh, originally we have 0 to 15. And we cannot have between galaxy 1 and 5, 0. It means that you have to probably this one located in here, because originally we have distance between galaxy 1 and 5 is 15. Therefore, because of that, these dimensions are gray out here. We cannot say, but we put it this number here on this column, second column, 0 to 15, to show how this activities goes. But we cannot put, this is meaningful because stretch, we cannot make it this rubber band become 0 in length. But we have to start from somewhere, that we start from 12 and after. And here, the location of the galaxy 1, always we assume 0. And when we stretch it, we calculate between galaxy 1 and 12, the distance between galaxy 2 and 3, 2 and 1. How much it is in 2 and 1? This is 2 and this is 1. It's about, uh, before here, 3 centimeter. We put here 3, and the second one 6 and 9. This is exactly the dimension that we have originally before stretching. 3, 6, 9, 12, and 15. Therefore, the first row that you see it is already there. And the third one in the 15, we assume that a minute passed and we see how much it grow. And therefore, we are assuming these numbers accordingly based on that stretching that we have 15 centimeters, 18, 21, 24, 27 at the end. Therefore, that's item that we have it here between the galaxy 1 and galaxy 5. And we measure the distance between the galaxy 1 and galaxy number. It means that here galaxy 2 and 1, galaxy 3 and 1, 4 and 1, and 5, 1. Therefore, when we complete this one, these numbers has to be filled out. We had some number, you see it as an example, we put it here, just but you can do it. Your numbers may not be exactly the same, but it's gonna be similar or very close. When you do 1 minute past each other and expand the universe from 15 to 27, you're gonna measure it and write it down on the table. But two things important here to consider. One is that when you modeling this universe expanding, originally was like that, and then gradually expanding on constant universe, constant rate, it means that you have distances between the each point is changing due to the time 1 minute, 1 minute, and then uh, the the things that we're gonna use in here, that's very important that it's gonna show on this constant value. Remember on the cosmological redshift that we have, we define it Z is equal redshift, uh, uh, whatever wavelength is shifted, and based on the wavelength that we have now. We see it. Therefore, this change of the wavelengths is called redshift spectrum that we had, and we showed before on the example on I think on the lab 7. Let me go show it lab 7 as well. What we had. If we go through lab 7, this is the one that we measure it at the end. What the redshift was. We measure it based on the numbers that we get from these curves on the lab 7. Let me see the curve. Yeah, here. Whatever redshift that we measured on each of the curve, this is the wavelengths based on the 21 centimeter the uh, constant rate that we have 21 centimeter electron cosmic ray, and we did that. But here on the lab 8, instead of the wavelengths, we're doing the distance between the points here, and how they're going to be connected. That's a simple way, that intuitive way that Skynet University use it here. We assume that uh, wavelengths that we're going to measure, we cannot make a we don't have any ruler that measure the distance between the galaxy and us. But we're going to use an intuitive way that we're using this wavelengths equal to a constant number times distance. And also same thing, when the emitted wavelengths comes, and we receive this one right now, uh, at that time, for example, assume a million light years away, that light is expanded on the universe. Then to get the, if we know the distance, we can get the wavelengths accordingly based on this formula, simple constant formula. And now, right now, we have the same thing. If we receive it redshift right now, this wavelength that we recorded on the curve that we see it on the lab 7 is equal to the constant times the distance now, because the distance is changing. And why it has happened? This is based on this concept that we learned here. Uh, the space is expanding, therefore the distance is changing. And when the distance is changing, that shows the um, cosmic wavelength. The wavelengths are also expanding. Therefore, the expansion of the universe is equal to the expansion of the wavelengths. And because the wavelengths is expanded, we can calculate the distance between any 2 points on the universe. And because of this concept, very simple concept that we are assuming uh, this distance and wavelengths are equal to each other, this is trigger or understanding how we're going to do this lab in here. Therefore, this is basic of this consideration. Then we put the on this equation instead of the lambda now, we put it constant in the d now. And instead of the lambda d then, we put it constant times d then. And instead of the lambda d then, also same thing. And then we cancel out the constant from the numerator and denominator, and the simplification, it comes here like this. Therefore, to calculate the cosmological redshift z, we needed to calculate the distance now minus distance at the past divided by distance at the past. And this is a very basic formula that we're going to use the constant cosmological redshift for the galaxy that we have on the rubber band universe. But this one is approximate. This method that is provided here is approximate, but it gives us very good indication in the hands-on activity by rubber band how to calculate the Z values very easily without having sophisticated astronomical tools. What we do here, and here on this data table 1, the one that you see it on the what do you call it, the yellow part, you see it, some of them is yellow part is identified here. This is now. In the after you expanded the rubber band from 15 centimeter to 27 centimeter, this is now. Whatever you see it on this row is now. And whatever you see it on the yellow, it is then. Whatever the expansion happened, and then the wavelength is scattered and emitted to the us. Therefore, originally was 15, right now is 27 on Galaxy 5. And Galaxy 4, it was 13.5, and right now it's 20.25. Therefore, this is for Galaxy 3, 10.5, 13.5. These numbers are you calculating yourself, and values that you have it on this diagonal, it's going to show D10. Therefore, whatever you have it here, D10, is the one that you see it on the yellow section market on the table, on this here, as you see it. And D now, the last row of the table. D now, all the values that you see it on the last row. Then we see, therefore, this first activity is that you just expanded the rubber band 3 centimeter every minute and fill it out this table. That's simple hands-on activity. And then you can, after you're done, you can take a measurement for the Z shift that we're gonna go on table 2. But before going that, we have some activity to show we have to prove that. For example, you may ask question why I recommended to do 1 minute every 3 centimeter every 1 minute, and how we can confirm these values that we have here show that the expansion of the universe is constant rate. That is one question, and that is valid. When you do that, some activity, you have to ask yourself why this is constant and why it is happening uh, in this configuration. Although you said we said every 3 centimeter 1 minute, but how we can justify that is constant? For that reason, we're gonna make a graph like this. And as you see it, the slope of the graph is constant. It shows that expansion is constant. What you need to do, you take the beginning, whatever on the example it shows here, beginning from time 0, distance between galaxy and 1, 5, versus time, you calculated that one. Whatever you're gonna do, you're gonna go to this website, Astromancer, and yes, Astromancer, new. And on here, we're gonna use. Do you see the Astromancer on the screen? I can hear.
Yes, we
Okay,
do.
yeah. Therefore, you just go here, the curve, and you may see some random numbers here. You delete those. And then whatever you recorded on the X and Y, you just bring it here. For example, let me go here again. We'll say between Galaxy N1 and 5. Which one is representing Galaxy N1 5? This is this values here, the last column. And what's the time? 0 to 9. Therefore, you go back to the Astromancer. Where was that? Yeah, here 0, 3. You can copy on also, but I'm just typing to show you how this is time that I putting 8. Sorry, let me go back to make sure that I didn't make 3 every 3 minutes. 18, 21, 24, 27. Okay. And then on the lab 8 last column, 0, 3 again to 27. 0, 3, 6, 9, 12. As you see, the graph is already constant. It shows, the numbers also shows. You have the same number X and same number Y. And here it shows that how they are constant each other. And one thing that you have, sorry, I might be a, let me see, I copy, I go. I think let me see. Yeah, that's correct. Okay. Here you can identify different curves. So for example, this is curve 1, curve 2, curve 3. If you have different curves, you can identify in here. But at the moment, we're just gonna use this one. And this is very good option that provided for Astromancer. You can add it this graph as needed, and you can edit the graphic titles here. For example, you put the redshift um, curve or whatever we have here. Let me make sure that I put it correctly here. Distance between galaxy 1 and 5, yeah. Edit distance between galaxy 1 and 5. And then on the x-axis going to be time based on the minutes, and y it's going to be distance based on the centimeter. Maybe no, this one, that here. Distance, centimeter, time, minutes, and the title on the top is redshift curve, distance between galaxy n 1 and 5. And this one clearly shows that its expansion is a constant rate. If the curve is like something different than this on the other activity, we're going to see it different. And therefore, when we have it here, is the universe expanding at a constant rate? Yes. And why it is yes? Because the curve has this line has a constant line on the time and distance. Okay. Therefore, here, as I mentioned, what is the D then and D now means on the table that we have it. And for the second table, we're gonna use the view from the galaxy 1. It means that distance between the galaxy 1 and different galaxies, we're gonna check it here. This is different galaxy 1, 2, 3, 4, 5. Distance between galaxy 1 and itself is 0 always. We don't need it to provide here. Distance between galaxy 1 and 2, 6. These numbers are calculated based on the numbers that we have on the table 1, this 2. D then is the one that is D now is the one that we had it here at the bottom layer. 0, 6, 7.5, 13.5, 20.25, as you see it here. D now, 6, 75, and 27. And D then, it is based on the galaxy 2. 6, 10 till 15 is the one that you show it here on the yellow tables. 0, 6, 10 and a half, 13 and 15. And therefore, you're putting here. And then calculating a factor here. How we can calculate um, the what you call it, the redshift? We have some formula here provided. What's the distance between distances traveled by the light? Distance traveled by the light is always equal to the distance that we have times the correction factor. That correction factor, we call it the luminosity distance. And this luminosity distance is the one that we're going to learn on OPIS. And you learn one of them that in this lab 7 and lab 8. And we're going to learn another ones on the lab 2 to lab 5 on the OPIS 1 and 2. This luminosity distance means that whatever we measure the distance related to the luminosity of the object that we see it. And those is the one that is helping the Hubble law to create how the light is traveled. Therefore, based on that, we create a concept here. We call it DL. This is DL is equal to the d times correction factor. We approximate distance of the light travel from galaxy 2 and 3 or 5 till 1 by averaging two distances. Whatever distance we measure it now and whatever we measure distance when the light is sending to us. Therefore, we're just adding these two together, 6 plus 6.5, 75 divided 2 is going to be uh, one number that you don't see it here, but that's the number we calculate first. Then you apply it times the correction factor. The correction factor is going to be d del now divided by dn. And for example, in here, for first one, it's going to be 675 divided by 6. It's going to be around 1 point something. And then correction factor, you're going to multiply by the average of the distance between this and this. 6.75 plus 6.0 divided by 2 is going to be 6.375, something like that. Then times 1.1 that you calculated, and you're going to get this value. And when you get this value, you're going to see the formulas. You're going to get the z values based on this formula. It's going to be d now minus d then divided by dn, d then. And you're going to see numbers 0.12, 0.28, 0.5, and 0.8. These are numbers are sample. You may get not exactly the same, might be a little bit different. Each individual may get different numbers, but that difference is not important. The important part is that when you come to graph this one again. In this example, you just graphing the luminosity distance, demonstrate distance. What is that? Is the one that you draw it here on this value here, dl. Because of that, we call it dl. L comes from luminosity, d distance. And this is a dl, and this is redshift or values that you calculated on the last column of table 2. Therefore, this is x, this is y. Therefore, whatever numbers you're going to get it from here, you graph it on the curve. Then I go back to the curve, and here, go to the website again, come to the curve. Instead of the first curve, I do it the one we have it right now. And here, let me see the values, 7.17, 717, and 15.4. Let me delete all of them first. Delete 7.17, 15.4, 5.3, and the last number 37.8. 37.8. Okay. The redshift 0.125. Okay, then next one 286 and 0508. 0508. As you see at this graph, also it looks like a constant, but it's not very constant because it's just curved in a different way. And this picture shows better. Probably here, as you see it, the graph is not very constant in the distance that we had it here versus the one that we had it, it shows differently. And let me do it a different way. And oh, I forgot the 0. That's the problem that we had. Insert row above. It doesn't work here. I think I have to shift it a little bit below. Yeah. I forgot the first one. 0 and 0. There's better picture. Here, as you see it here, is direction gonna be similar to one that you see it on this one. That here you see 0.8 and 37 something, and here the same thing, 37 and 0.8. And this one shows that how you can create this activity on here. And Hubble law state that farther away the galaxy is, faster it appears to us. And this is a galaxy that we have farther away. And this one, it shows that exactly we have more redshift. Whatever redshift is that, what's the definition of the redshift? As you see it on the previous lab, on the lab 7, we defined it redshift is equal to the velocity divided by velocity of the light. Let me see where it was, redshift, and here, formula. As you see here, we calculate the redshift, and then at the end, we calculate the of different values. Sorry, on the 8th, chapter 8 we had here. Let me show it on this sense. Yeah, here. Here V is equal C times Z. Z, whatever is, it shows Z is equal V velocity divided by C. Therefore, in here, as the curve, it shows 0.8. It means that whatever galaxy is far away, its velocity is 80% of the uh, speed of the light. And this shows exactly what it means on the Hubble law. This table 1 and 2 clearly shows us how we can calculate and measure the distance. Instead of the wavelengths, we use the distance, and we can measure it accordingly. Is that have been able to replicate Hubble law? The answer is yes. You actually, with this simple rubber band universe, you can calculate this simple way accordingly. And the next ones is also same way. We're doing differently. First one, we just observe it based on the galaxy 1, or galaxy 1 is the point of the reference, and we calculate distance from galaxy 5 to 1. On the next procedure, you're going to do the same, but in here, you assume that instead of the putting galaxy 1 um, on the previous object, here, repeat this section B, but this time measure the distance between galaxy 2 and each other galaxy on the table 3. Therefore, viewed from the galaxy 2. And then we do the same thing on the constant, this is constant rate, same as the table 2 for the table 4. And the same thing, we do the graph accordingly. You see the graph is almost the same. We can compare it with the Galaxy 1. It doesn't much have a difference on here. This one, we show it on the table 1, 2, and 3, and 4 compared to the 1 and 2 galaxies. You can do it for all others, but we don't need it. This 2 is only provided to give you indication if you choose it, Galaxy 1 or Galaxy 2 as a point of reference. It doesn't matter. It gives you almost identical resolution. Two observers in Galaxy 2 has this much right to say that the center of the expansion of the observer in Galaxy 1? Answer is yes. And therefore, either you look through Galaxy 1 or Galaxy 2, you think um, the expansion of the universe are the same. And these two comparison, we can say it. Can anybody claim that to be a unique center of the expansion, either on the galaxy 1 and 2? The answer is no, because it shows that either you located on galaxy 1 or galaxy 2, you can see the expansion of the universe at the same rate. And it doesn't matter, there is no center of the expansion exists. And that's kind of things that shows a very kind of iconically by this graphs. When you expanding the balloon, all the galaxy are gonna be far away from each other. Therefore, it doesn't matter where we are located, there is no center of the expansion. There is no kind of there is no location of the center of the Big Bang, we can assume, or center of the universe. This is meaningless because of this concept of the expansion of the universe. And by this simple example, we can show how that expansion works and on the constant rate. And you can do that similar way for the deceleration universe and also the same way for the accelerating universe. But the difference is that here on the constant rate, what you assume that is galaxy is going to be um, at constant rate of the 3 centimeter per millimeter it happening. But here you can assume a decelerating way. For example, here uh, time that you consider it was before was 0, 3, and so to 9. But here, instead of the 9, you divide it by different method. 0, 0.7 minute, 0.1.7. This is a number you're choosing in randomly. And you can calculate different way. Instead of the 1 minute or so, instead of the 1 minute, you can assume less than one. 0.7 using here, you can use different methods, 0.6 or 0.8, whatever you need it. And also for the expansion, you can do it the same way. Here, for example, we expanding, accelerating on different way. If you look through this table 7 versus table 6, table 5, and versus table 1, you see the difference between the constant rate. Here is constant 0, 1, 2, 3. This rating is, as you see it here, 0.7, 1, 2, 7, 3, and this is less than 1. It shows the decelerating, and this one is also accelerating. You assuming the table, it goes in um, more than 9 minutes. This one is now right now. Therefore, this is very simple example that you can show it how that's gonna work here. For example, this is constant, and this is show expanding, and the other one it shows the descending. As you see it, when it is constant rate is on the middle, decelerating on the left up, and accelerating lower down. And when you come all of them together, this gonna show the um, checking to see expansion of the universe either accelerating or decelerating. But as you see it, this is the data showing on the actual experiment on the universe. As you see, most of the points are on the lower point of the middle line. And that shows that universe is accelerating. Why we can say that? Because as you see it on this experiment, when they accelerating, most of the point is lower than the constant rate. And as you see it here, most of the dots is calculated based on the actual real measurement on the universe, based on the supernova type A. It's gonna be all of them. Not you don't see it much on the left side of the curve, and that shows us that universe is accelerating. Any question? This one a little bit might be time consuming, but it gives you, if you go each one of them separately and calculate it, and each of them graphs, it shows how the curves is going to be rotated if constant going to be like this, and the accelerating on the lower part and decelerating on upper part. Because when you just decelerating, it means that distance is not going to go much compared to the redshift, and accelerating, it's going to be distances going to be go farther apart each other. And based on the current data that we have, it shows that universe is accelerating on the expansion. Any question?
We're at the top of the hour too. And really, I hope this exercise, it seemed very complicated, but the physics implication of this is very intense, the astrophysics of this, because this is, we're looking at redshift over large distances. And also this relates to special relativity also. So I'm kind of glad for this exercise because it's some very, very deep concepts. I'm going to share one image real quick. I know we're out of time, but this actually is very much related, not to the rate of expansion acceleration, but I can find it here. It's a cartoon I found online that it's a question we deal with also. This is one that Einstein over 100 years ago was thinking about, which is very much related. What we have is somebody on the Earth and somebody far off on a rocket ship. And in this example, we could think of, do we see the same thing? And the deal is, if the space is moving, if the rocket ship is moving, then all the actions in that space should seem faster than what we see on Earth. In relativity, we find we can actually do it without the great distances. You just speed something up. When something's traveling at a great rate, it is in a different space time. It's like it's a million light years away. It's very similar analog. This is special relativity, where what we're actually doing in this is redshifting, and more general relativity or dealing with gravity. But just the parallels are just amazing. The question he was asking, is somebody were to fire a photon torpedo at almost the speed of light. Here on the Earth, it wouldn't break the speed of light. But if you did it on this spaceship, which is almost going the speed of light, you should break the speed of light. And it doesn't happen like your rubber band. We see that everybody's kind of measuring the same thing, but in a different realm, in a different space time. So when you are looking at things, stars that are very, very far away, that red shift means everything's shifted, and you can't exceed the speed of light. And when we do the math, it doesn't come out greater, but the math is actually very complicated. So this is a very simplistic exercise, which I never thought about using a rubber band to do this, but it really does show, like, from different places in space, different aliens, civilizations on different stars look at us, we look at them, that we're being affected by the space between us, about the moving space, the expanding space. We don't see the same thing. So it's like that thing, if you're driving 50 miles per hour for 5 hours, you should go turn 50 miles. Well, if you're looking at somebody in another star system who's far away, you wouldn't get 250 miles. It'll be shifted. There's all this shifting going on. And the world is a lot more complicated, a lot more wonderful, I think, if when we get into this craziness, because that's how it is. We just live in a very slow world, in a very small world, in small space, where things are pretty simple. So hope I didn't lose you there at the end, to overcomplicate it, but just I like this, because remember this, because maybe later on in college or in physics courses, when we talk about relativity, this is what it's about. You have a heads up on how these pieces fit together. So couple little notes real quick. Tomorrow night is a star party at Marvin Ridge between about 8 to 9:30. We'll probably go to about 10. And Also, I'll probably get out the radio telescope. I might get that horn out too. We might try hooking that up to the laptop and see if we can't listen to some stuff at the 21 centimeter, which is about 1.4 gigahertz. Which, if we can dial that in with the SDR unit, we might be able to listen to the Milky Way if it's up when we're up, which I think it is this time. So, a little plug for that.
Very good, very good. And also, I would like to say this activity that you see at table 1 to 8, it's mo one of the most comprehensive and very active uh, uh, kind of mathematics and tabling and graphing on entire lab 1 to 9. You don't want to see all of them at the other labs on the 405 and 356. And this is kind of a little bit maybe time consuming. But if you had any question, just do not hesitate to ask in the email or when you do the activity. When you do activity and you learn from WebAssign, you feel it more comfortable than the one that I explain it for you. But I try to explain it some major items that you may not see it on the um, kind of expression on the WebAssign text, and I hope I catch it the major items that is important. And if you had any questions that when you do the activity, just please do not hesitate to ask in email or on the web, what was that group me account. Yeah, therefore, John and I here, we can answer your question and help you.
Yeah.
Okay, any further question, guys?
Hey, thanks everybody for joining us tonight. And feel free to swing by the room if you want to talk a little more about special general relativity too, which is kind of a tangent of this. Other than that, looking forward to seeing y'all. So thanks for joining tonight.
Very good. Thank you, everyone. Have a good night and see you on Thursday.
Have a good one, Professor.
Have a
I'll
good.
see you tomorrow, Mr. Taylor.
Thank you.
See y'all. Have a good evening. Thanks.
Good evening.